So first, I want to thanks to organizer to giving me this kind of nice chance to talk. Yeah, today I will speak about the higher linear series of projective variety. The title of my talk is Upper Bounds for higher linear syzygies of projective varieties. Yeah, this is first talk. Yeah, this is joint work with by Sejong Park. Yeah, so today I will start by some brief introduction about what is the subject and what is the syzygy and Bethe number means. So our object is embedded projective variety of dimension n and codimension e. This is maybe same notation with Professor Noma. Our algebraic closed field and characteristic is 0, and we did not and the degree of x is d and codimension of x in Pn equal e. So to study this embedded projective variety, there can be many ways, but one of my favorite way is to think about this one using the free resolution of the things. So for given variety, we can think about a homogeneous coordinate ring in here. So if let S is the polynomial ring with n plus 1 variable, then we can think about the ideal, which is define and cut out the x in this ring, and we can associate this quotient ring is the homogeneous coordinate ring of x. So we can think about of this ring, the minimal free resolution of this ring. Then this might can be written like this one, and this is f1, f2, fb. So this is each fi is graded. So our coordinate ring has natural grading structure. So this is graded free S module. And this each map difference. For example, at this level, this length is the number of the minimal generator of the Ix. And we can think about the kernel of this map, and we can set the minimal generator of this kernel, and we can continue this process, and so on. Then the finite termination of this free resolution is guaranteed by the Hilbert-Syzygy theorems. So we can write each fi is follow And we can denote the length of the graded piece of each Fi is beta Fi, and we call this beta Fi is graded fatty numbers of X or Sx. So in the lecture of the Giorgio, Professor Ottaviani says this beta ij is give generally more refined information than the Hilbert polynomial of X. And I have also one more remark is here. There is, for this beta ij, so if we consider the Tor module, then this is equal to the dimension of Tor I stores of I plus d degree pieces. Yeah, this is. So there is two major, I think, major two convention for this beta ij. One is by Green and Ayin and Lazarsfeld. This notation is this one. And another major conventional notation for this beta ij is maybe used by Eisenberg, Schreier, and for example Ottaviani. They denoted this beta ij is beta I comma I plus j. So this is two major convention. So in this talk I will use this GAL notation, not SO notation. But but if you run the Macaulay program to compute some Betty table of some module or a variety, then the output diagram is same one. So if the GAL notation, then Betty table is just so I's column and J's row denote beta ij in this notation. But with this ethyl notation, they in Macaulay 2 gives table like this is I, and in this J's row they put here beta, not beta ij, but beta I plus j. So the final form of both conventional notation is same. Okay. So let's denote the Betty table. So we can, if we think about the table of this beta ij, then this gives more useful information, many useful information to X. So we can denote this Betty table of Sx is bold Bx. Okay, so so you can know with this resolution, the first Betty number is just 1, and here beta 1 comma 1 is so number of quadratic generator. If we assume our X is non-degenerate in Pn, then there is no linear form of this idea. Then at that situation, automatically this is 0, and this is refrigerant 0. Then this is the first quadratic generator, this refrigerant, and beta 1, 2 represent the cubic generator of the ideal, and here beta 2, 1 represent the linear relation of the between the quadratic generator, and this is representing that one, and so on. So we can roughly draw some Berry table of projective variety is in some sense, okay, sorry. So if our variety is cut by the quadratic equation, then okay, let's think about following a table. So in last 30 years, there is quite many research about the syzygy of the projective variety, and especially there are many results about the petit number on this law. So especially we call this part is the first linear strand of Berry table Bx. So today's our topic is also on this Berry number on this first linear strand. So as you see, this first linear strand is characterized by two pivotal number. So we call this is AX and this is BX. So AX is so if you know the all Berry number greater than so in as Professor Ottaviani says, NP property, if NP means so all beta I comma j equal 0 is I is from 1 to p and j is in our rotations, then j is greater than equal to 2. This is NP property. So AX is denote the maximum number, the highest number which NP is satisfied, and this is BX also denotes the length of this first linear strand. So by these two pivotal number, we can characterize the first linear strand of the Berry table. Okay. So there is someone who is not familiar with this kind of Berry table, that I will give some very simple example. So if we think about some residue field, if we think about the resolution of this residue field, then this is generated by the the whole idea of whole variable, then this resolution is given by the Koszul resolution. So in this case, the very table is just given by the binomial coefficient So in this case, very simple, very table. And another simple case is if we can think about the complete intersection of two quadrics. Then the very table is just given by the three number, the 1 and 2, and their causal relation here. So so this in this case very simple. And another famous case is X is the variety of minimal degree. So minimal degree means the degree is equal to the codimension plus 1. Then in this case, the Berry table can be computed by using Egon-North complex. Then we can compute by this formula.
In the second case, AX is 2?
So in this case, so we start here from 0. So 1, 2. So in this case, AX is 1, and BX is 2. So if our variety cannot cut out by just by the quadric, then AX equals 0. And so in this case, AX equal 1. Bx equal 2. And another known case is if our variety is arithmetically quadratically and degree is next to minimal, it means codimension plus 2. Then in this case, this is classically called by Del Pezzo, and for this variety, the Berry table is given by this formula. So E plus 1 choose 2 minus 1. I's Betty number is I times E plus 1 choose I plus 1 minus E choose I minus 1. And at E minus 1 homological degree level, this is 0. And codimension E level, this is just 1. So in this case, this is Gorenstein, and this Berry table is symmetric. Diagonally, this is symmetric Berry table. So there are many problem and conjecture concerning this first linear strand or AX and BX. For example, Green conjecture, many problem or conjecture on this AX or BX.
What's the number? The I times E to the I plus 1 minus 1?
Yeah.
No, that's
yeah. I times E plus 1 choose I plus 1 minus E choose I minus 1. I'm sorry. Yeah. Yeah, so in this syzygy world, there are many many famous problem conjecture concerning these numbers. Conjecture on algebraic curve or Eisenbart-Goto conjecture on the regularity. This conjecture is not just concerning AX and BX. This is concerning the height of the Betti table. The height of Betti table is correspond of the regularity of the variety, and and we can also think about Mukai conjecture on concerning AX MP property. So, and now I want to more some non-classical result of this AX and BX number. So, my first motivation to think about this kind of study with 시종과학 is original problem is regularity conjecture. So I think about how this Betti table behave under, we are using consider like Professor Noma inner projection. So how they behave under this inner projection operations. But we know the behavior of this first linear strand also very interesting and important to consider the structure of the variety. Then we can keep on this study. So our rough observation is this one. This is starting point for this upper bound. So our observation is following. So if our X has more quadratic, it means the beta 1 1 or H0 is this number is quite large. Then the syzygy is better. Better means better or simpler. Simpler syzygy. This means our number AX is higher. So the linear syzygy go further. So this is supported by famous classical result. So first one is Castellubo or Fyodor Jacques. different method, or myself and Kwak. We can approve this many different methods. So this number beta 11, the number of quadratic generator, is bounded by this number. The codimension choose 1 plus 2. And also we can classify the equality case. So this is equality holds, means X is degree of minimal variety of minimal degree. And this is also geometrically classified 100 years ago, maybe, Del Pezzo and Bertini. And in modern times, Eisenberg Harris, they are classified this variety. And there is also, next to minimal case. So I heard this is due to Fano, but I don't know original reference. Just maybe Lvovsky, maybe student of Jack. He in his paper he mentioned about this result, but I'm not sure. But if so, unless unless X is variety of minimal degree, then our beta 11 is bounded by this number. And we can also think about equality case. So boundary case is equivalent to is X is Del Pezzo. Here Del Pezzo means, as I read before, ACM and degree is E plus 2 next to minimal degree. Okay. So you see, if the variety has many quadrics, then their syzygy is given by this table. The syzygy is getting simple, and the AX number is go higher. Okay. So we questions. Okay. So our first question is, can we generalize this result to the not just to the number of quadric, to the higher linear syzygy? So first question is, can we
Del Pezzo.
There you have only also some bound D, no? So for example, if E is equal 1, only the surface is Del Pezzo.
So this is in some sense in our talk. Del Pezzo, we define. This is a little bit different. Classical Del Pezzo. Okay. So first question is, can you generalize this result to the result on the higher linear syzygy numbers? And and another question is, so from this rough observation, what is least number lower bound. Lower bound for beta I plus j to hold NP property. Yeah, so for given P or for given AX, to achieve this AX number, what is the lower minimal number of this beta ij are? So this is our basic question for this study. So for this question, I think we should think about some reduction method. So classically, in the classical algebraic geometry, projective geometry, the hyperplane section method are very often used. But for this question, we think about some inner projection method. So I'd like to shortly compare between these two methods. So here is hyperplane section. So our x is, as usual, in Pn. So if we take this section, then this belongs to the Pn minus 1, and the codimension is preserved. Codimension is equal to the original one. So this means the dimension is decreased by minus 1. And the degree is also preserved. And if we determine the delta x is degree minus codimension minus 1, this definition is equal to the Fujitsu's delta genus definition in our embedding case. Then this delta also preserved. And now if we think about inner projection, then we take some general point of x. Then we can think about the Zariski closure. We denote xq is Zariski closure, as Professor Noma explained. This is also belong to n-1. Then this codimension, in this case the codimension is decreased by minus 1, but dimension is preserved, and degree also decrease by minus 1, for this is general point. So so the delta is also preserved. So so for some given problem, we can consider this kind of two reduction method. So I think usually if we taking hyperplane section, then geometrically this is getting better for example, for surface or curve cases, there are many known results. But for the equational viewpoint, if we reduce the section to the curve case, the problem is not so many reduced. Yeah. But in this method, we can reduce the codimension. So the geometry is getting more not better and getting more difficult. But in some sense, equational viewpoint or syzygetic viewpoint, in many cases, the situation could be better. Okay. So we are using both method. So let's see how to behave the syzygy under this inner projections. To study the syzygy of inner projection algebraically, we need some mapping construction. So I will briefly introduce what the construction is. We call this is a mapping construction. So this is our point with some suitable coordinate change. We can assume this is 1, 0, blah 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 0, and so V is the vector space of n+1 variable, and W is vector space. So one basis, one variable is eliminated. Then we can also consider their symmetric algebra. And M is any graded S modules. And mu is just given by multiplication map by eliminated variable x0. Okay, so we can consider two graded causal complex. F and G, and the induced chain map by mu from complex G to F chain. Okay, so this is
S1 or
so this is given graded S module, but S1 is subling of S. Yep. So sorry. Sorry. I'm sorry. This is twisted by 1. Then this is degree preserving map. This is degree degree preserving map, and we can by the standard mapping construction. Yeah. Yeah. Then there is long exact sequence, such as this one. So we have this kind of long exact sequence. The meaning of the usefulness of this sequence is for given graded module, this is a way of connect the two Betti number. One is as S module and one is another S1 module. This is eliminated links. So this is one thing for our study. And another thing is a so-called partial elimination theory, ideas theory. We are write briefly. PI is This notion is introduced by Mark Green from his famous note about.
What is the difference of this exact sequence when you take the Q outside of X?
This is also hold for any Q.
Any Q.
Yeah, any Q. And M is any graded module. This is some algebraic construction. So in this step, there is no geometry. Yeah.
Q is just a point. Not
Okay. Okay. And what is the partial elimination idea? Is let's think about some consider a natural filtration of S with respect to our variable x0. It means this filtration. So this is S1 and next is S1 direct sum x0 times S1 and next one is x1 times S1 and x1 square times S1 blah blah blah. So denote this is F0 and this is F1 and this is F2 and this is, let's denote F infinite. So we can think about the filtration of S like this. Then our Ix is the ideal submodule of the ring S. So this filtration also induce some filtration on our Ix. So Then we denote this is K0 tilde Ix, and this is K1 tilde Ix, and this is K infinite tilde Ix. Yeah. Okay. It is right. Right. Yeah. Okay. So then, so I will. Yeah. And yeah, and you can consider this diagram. Yeah, this is projection to the ith component, and just this degree shifting. Consider degree shift map. This is, and this map is P. Then our Ki tilde Ix is here, so we can think about the image of Ki tilde of Ix through P. So we define this image is, we denote Ki Ix. So this is inside of this ring, and actually this is ideal. So we call this is ith partial eliminations ideas. Yeah. And easily we can observe the following fact. First one is this is real. Actually, this is ideal of this subring. And second one is the K0 Ix is just the complete elimination idea. Yeah. In S1. So this define this ideal define the projected image, our X cube, and by the natural inclusion of the filtration, we know the K0 Ix is contained K1 Ix, and this is contained to the K2 Ix, and this one. And by the Noetherian property, in some final step, they should be stabilized. So we call this number S is the stabilization number of these partial elimination ideas. And this number also depends how we choose Q inside of X. Okay. Then there is some proposition of this number S is if our idea is generated by degree within D. So this means in Heisenberg notation ND1 property. Then if we take our Q is outside of X, then this stabilization number is at most D. And if we take our Q is some general, smooth general point inside X, then this is at most, this number is D minus 1. And second, also the stabilized idea, this idea reveal some local geometry of Q. So if our Q is in X, then the stabilized idea KSIX is equal to the idea of the tangent cone of X here. So for example, if D equal 2, so our varieties N1 satisfy N1 property generated by quadric, then our number is S equal to 1, less than 1. So the first partial elimination idea, and if we take Q is smooth point of X, and this is just given by the E linear form, which define the projective embedded tangent space of X at Q. So we can calculate the syzygy of this idea by the linear causal relations.
Can you repeat what means L1, LL?
This is defined the n-dimensional linear space. This cut, this is codimension. This is codimension.
LE is the first one. Okay.
This is linear form. Linear. So our strategy to connect the Betti number of original variety and to the Betti number of the projected variety is this one, the outline.
KIAS is ideal of S21,
this is ideal.
Right side is ideal of S. It's actually so. Some right side is the ideal of S.
But we can also interpret
so
this.
We can think left side is ideal of S.
But
It's the ambient space is a little bit confusing to me.
So there is no problem. So if our X is here, so this linear form cut the projective tangent space, and in the this is Pn and this is Pn minus 1, and this is image. Then this idea also defines some linear space here. Actually, this is the image of the exceptional divisor. We can interpret the inner projection using the blowing up, and this is the image of the exceptional divisor. Yeah, so this is image of this one. So yeah, we can interpret in both space. So here is our Ix for given S idea. So using the elimination mapping consequence, then we connect this one between the Betti number using this construction, we are connecting Betti number of the S1 module, and from here
Ix cube left side, right side. Ix cube or Ix?
Ix. It's just the Ix. We should go using two step. So if you remember, yes, this mapping cone is for same module but different base ring. Yeah, so the mapping consequence tell how they are related. And first step is this is first step, and so the S1 module of original variety and the projected variety, we can also connect this is using by this partial elimination ideas. So if we know the syzygy of these partial elimination ideas, then from that information we can also relate it and compare these two Betti number. So we are connecting these two numbers. So so I have another chance to talk on Wednesday. So now I are writing just the our main result, and the proof will be given on Wednesday. Okay. I'm sorry.
Ix, if we consider Ix as a S1 module, is it finite generated?
Not finite generated. If our Q is outside X, then this is finite generated module as S1 module. So Ix or this is finite generated S1 module. But if we take our Q is inside X, then this is infinite generated module. But we can still using this kind of mapping construction and the theory. And in fact, so funny thing, interesting thing, just appears some low degree level. Sufficiently high degree level, then all situation goes to be some stabilized situation. So there is no information. So interesting information is to happen in just first low level.
I don't understand. If it is infinitely, this Betti number on the right corner could be could go to infinity.
Yes.
And so still the
So I explain. So for example, let's consider this sequence. This module sequence. Then we have total long exact sequence this module, and from by eliminate mapping construction, we have some information on this middle term. Yeah, and we want to know some information, Betty number information of this first term. So yeah, this is consists of 3 terms. So at least we know the 2 terms. So we know some information on this, and we should analyze the third thing. But yeah, with the partial elimination idea. So yeah, I can show you there is some sequence. So there is some natural sequence of partial elimination ideas. So this is twisted -I-1. Yeah. This is some natural sequence. So if we know from the geometry of our projection center, if we can calculate the syzygy of this one, then yeah, we can relate these 2 syzygy. In I=0 case is our desired case, the whole eliminated idea. And this is also if we iterate this process, and this goes to our original idea Ix, because this is k infinite Ix. So yeah, using this sequence, we also can map out here. Then iterate this process. Then this syzygy is approximate to this syzygy. Yeah, from this syzygy of this partial elimination idea. So we know every Betty number, each graded piece, degree piece, and we can calculate this one. Yeah, and finally this one. Yeah. So, sorry, the time is already over. So I will finish it just to introducing our result. Okay. So if our X is satisfy NP, or in some general case N to P, so yeah, let's say so this, let's say, yeah, for some AX, so then we know some natural embedding, natural injection. There is a natural injection of this is total module. For every I is less than AX minus 1, and J is every J. So consequently, so beta IJ, this is less than 2. Yeah. So this meaning, if our variety has some property n to a, so up to 8th step, just the linear syzygy, the syzygy consists just linear one, then yeah, the first a minus 1 part of syzygy is come from the here. So this is already embedded one of the higher syzygy, upper syzygy. And this also can give some number of the AX is bounded below by this number. So Q is smooth, any smooth point. Okay. And the second one is if we concentrate on J equal 1 case. So J equal 1 case is first linear strand. Then we can say more. For example, without some emptiness assumption, we can say just first linear strand is this beta Berry numbers is not be greater than the Berry number of the X for all I, and this formula is very important for any I. Original Betty number is bounded above by this formula. E represent the codimension of original variety. And so I equal, and this is equality holds for I is less than AX minus 1. And another nice thing for this kind of series of inner projection, then the length of whole Betty number, it can be computed by the arithmetic depth by the Osland-Bussbaum formula. So in this case, the arithmetic depth is preserved. Not every case, but if our stabilization number S equal to 1. So this means so our near our center Q, this X is generated by the quadratic equations. Then with respect to this Q, F equal to 1. Then these two depths equal to they are same. It means by Osland-Bussbaum formula, the whole length of Betty number is decreased just by 1. So this is last result of today. So with this, especially this, fundamental inequality, we can bound. So X is any variety, then the Betty number in the first strand, beta I1, I comma 1. For any variety, this is bounded above by the Betty number E times I plus 1 choose E plus 1 choose I plus 1. And this Betti number is just the Betti number of the minimal degree variety. And so, yeah, and furthermore, yeah, the following are all equivalent for this variety category. Is X is minimal degree variety, and X is, in Castello-Van-Montfort sense, too regular, and beta 1 1 equal to this number. So this means, yeah, this inequality achieve equality for I equal 1 case. And also, so one of these beta ij equal to this number for some I. Yeah, and all of this beta ij achieve the maximal bound. These are all the equivalent. Yeah, so today I stop here.
Question, comments?